Now let's think. Okay, we said the temperature. It impacts. How does the temperature impact? Okay, we said this is our roughly our, if you imagine the microstructure. This is our, the bigger circle represent our so-called matrix or host atom. The red small atoms represent our so-called impurity. What type of impurity? Interstitial impurity. It goes from one location to the nearest neighboring interstitial site. But do you think geometrically it has to go through something like this, right? It doesn't magically go from here to here. It has to go something like this. And when it occurs, it still got to what? Push stuff around. Except it's not as big as when you do the direct exchange for so-called substitutional diffusion. Make sense? Then, if we consider the so-called energy perspective, initially, I'm sitting at a valley side. Afterwards, it also sits at a valley side. And typically, these two valleys have the same energy. Make sense? Because they are indistinguishable. But in between, do you see it must be sitting roughly something like this at a peak side. And from the peak to valley, we have this delta GM. This delta GM, we call it activation energy. We can kind of understand it as a so-called activation energy or migration energy barrier. If we think of the system free energy initially at here, when it's at this location, it sits at the peak. This energy difference, we call it a migration energy barrier from Gibbs free energy point of view. Okay? Then, from Boltzmann distribution, which tells us the proportion of high energy atoms. If all we have a large number of interstitial atoms, how many of them has the kinetic energy higher than this? All sits at here. That's the Boltzmann distribution. The proportion, we have many so-called interstitial impurities. How many of them have kinetic energy that is higher than this barrier? Or how many of them are sits at here? It kind of means the same thing. Would be given by this distribution. It's a probability. Exponential delta GM over RT. If we are considering 1 molar of stuff. Okay, minus sign. Which means the higher this barrier, the more positive my denominator my numerator is, this probability become, remember that's a negative sign, goes to 0, right? Because the higher this delta G, the more positive this delta G, I have this negative sign means my probability goes to 0. My larger the barrier, my probability goes to 0. But at the same time, the higher, if I fix this delta GM, the higher the temperature, the smaller this thing will be, the higher the probability, right? Okay. So the successful jumping frequency. Now let's understand the successful jumping frequency, that gamma term, we said it relates to thermal vibration. Thermal vibration we just said is mu. We can estimate by h mu equals kT. That mu, the successful jumping frequency would be mu, my thermal vibration times that low probability. Mu give us, okay, every item at any moment is trying. But among all these trials, the probability of overcoming this barrier would be given by this. Make sense? And that's our so-called successful jumping frequency. Mu is every attempt. Among all those attempts, for the previous example, 1 in 10,000, that's low probability, you are going to be have the kinetic energy higher than barrier, or you sit at here, which means you can go. Make sense? So that gives us the probability, so-called successful jumping frequency. And then this is what we have. The successful jumping frequency is mu times this exponential term. Within the exponential term, the numerator is our so-called, we call it kind of like a migration barrier in Gibbs free energy term. Okay, and then our diffusion coefficient, if we are going to rewrite it, remember our diffusion coefficient is 1/6 gamma alpha square, except now our gamma will be replaced by mu times this exponential term, 1/6 mu exponential term. Now we replace this delta Gm by, remember, delta G equals delta H minus T delta S, right? This is what we got. And alpha square, don't forget that alpha square. Okay? This is now our diffusion coefficient, 1/6 gamma alpha square. Alpha square is this one. This is the gamma term. And this term, because the numerator still has t, and some of the t can be cancelled out. So we rearrange. Do you see that? 1/6 we keep. Alpha square we keep. This mu we keep. But exponential term, this t delta x minus cancel. T delta x r t, do you see the t cancel become delta s over r? This whole thing become our pre-exponential term. And the other term would be exponential of minus delta h over rt. So now we rewrite the diffusion coefficient term. You see that? This minus delta hm rt become here. Remember, within exponential, the plus will be times of outside exponential. Do you see that? Okay. So if, again, now let's define some additional terms. If we define so-called d0, the pre-exponential term of so-called frequency factor, what is the frequency factor? We define the things within this square bracket. d0 of the things within this square bracket, 1/6 alpha square. What does alpha mean? Successful jumping distance, which relates to the lattice parameter. What is this mu? Vibration frequency. This exp term, the exponential term, tells us something about entropy and the gas constant. This is so-called our frequency factor. This whole thing pretty much the same for the same solute atom within the same system. And then if we define the so-called real activation energy, H term, delta H term, the enthalpy term, if we define that as Q, that's our activation energy, the enthalpy term, then we are going to rewrite the diffusion coefficient would be dB0. B0 would be the frequency factor times a exponential term of QD over RT. And this one relates what? This one relates the temperature impact on the diffusion coefficient. Honestly speaking, this term, actually the mu term, also depends a little bit on the temperature, but not as dramatic as this exponential term. Do you see the mu term actually depends H mu equals KT. That also depends on temperature, but that dependence is not as strong as this exponential term. So loosely speaking, we would say diffusion coefficient, quote unquote, exponentially depends on temperature, and that's primarily due to this 1 over T minus exponential. That's why I quote unquote exponential, because it's not direct exponential T. It's 1 over T, put a negative sign. Questions? So now let's look at some one particular example about temperature effect of on the interstitial diffusion coefficient. What we are looking at would be in BCC alpha ion, the ion that has a body center cubic structure, and we have a table that lists D0, what we call frequency factor, that has the same unit as diffusion coefficient, meter square per second, or in this case millimeter square per second. And also Q, what is that Q? That's what we said, diffusion activation energy. Okay, that's an enthalpy term. That enthalpy term. And we listed the numbers for 3 types of interstitial atoms. What are those 3 types of atoms? One is hydrogen, the other one would be nitrogen, and the third one would be carbon. And then naturally, as you imagine, which one is the smallest among all these 3 interstitial diffusion, interstitial impurity? Hydrogen, of course. And because hydrogen is the smallest, does it surprise you that it has the smallest Q, activation energy, or the energy barrier? No, right? Because the smallest, it disrupts the lattice the least. On the other hand, carbon versus nitrogen, carbon is valence 4 larger versus nitrogen. It has the highest activation energy. Make sense? And similarly, what you would also notice is the frequency factor, the D0 term. Which one is smallest? Also for hydrogen. Between all these 3, if you recall, the frequency factor depends on lattice parameter, but the lattice parameter or the jumping distance is the same for all these 3 interstitial species, right? But the entropy disruption term would be larger if the atoms are a little bit larger. Make sense? Because that's the frequency factor, that's the mu term. That's pretty much the same at the same temperature for all 3 atoms. And but then the entropy term, exponential delta S over R, that is largest if the atom is larger. So this is what we have. Okay, for the frequency factor and the activation energy for interstitial atoms of carbon, nitrogen, and hydrogen within BCC alpha ion. Okay, and you may ask, in reality, how do we get this so-called Q, activation energy or heat, and the frequency factor? How do we get these values? How do we get them from measure the diffusion coefficient? Well, if we remember, what is our relationship between diffusion coefficient D and the temperature term? This is what we have, right? It has a format of a so-called Arrhenius relationship. D, diffusivity or diffusion coefficient, is your so-called D0 frequency factor times that quote-unquote exponential term. That quote-unquote exponential term depends on temperature, right? That's what we said. The D0 has a very weak dependence on temperature. So with this, what's the relationship between D and T? If we are going to take so-called natural log, if we are going to take natural log, left side, right side, can you check? Left side become natural log of diffusion coefficient. equals natural log of d0. The minus sign comes to here, right? And then this is exponential, which is e to the power of something. And I take natural log, it's just this thing. Make sense? It's just within q over r times 1 over t. That's what we would obtain from taking the natural log of both sides. Of course, sometimes we would prefer to use, instead of natural log, the log with the base of 10, right? Going from natural log, change to the log based on the base of 10. And we would have a similar relationship, except this factor, we have 2.3 here. That's kind of roughly the conversion between natural log and the log with base of 10. So what do we get? If we are going to plot the logarithm of diffusion coefficient versus 1 over t, what shape would we get? In other way, if we're going to plot log d versus 1 over t, roughly what would the curve look like? Well, q is, for a given system, is a constant, right? R is also the gas constant, which means this guy would be constant. This guy is also. So if we plot log d versus 1 over t, do you see we are going to get something like this? It's straight, kind of a straight line for actual data points. Of course, your measured actual data points would vary a little bit. If we measure at one temperature, at another temperature, on this plot, the left side is higher or lower temperature. 1 over t close to 0 means the temperature is higher. 1 over t is higher means the temperature is lower. Okay, we get a kind of a linear relationship. And if we do linear fit, we get something like this, right? And the slope, what is the slope? Do you see the slope would just be, if we plot the logarithm with base of 10, would be just the q over 2.3 r with the minus sign, right? That's our slope. And what is the intercept? Intercept when 1 over t is 0, 1 over t is 0, this term becomes 0. Log d is equals log d 0. Okay. So in reality, how do we do? We are going to, in order to get so-called frequency factor and activation energy or activation heat, we have to measure diffusion coefficient at different temperatures, plot in logarithm of diffusion coefficient versus the inverse of temperature. The slope would tell us q, while the intercept at the vertical axis would give us the so-called frequency factor. That's how we can get those two parameters. And then you may ask, Dr. Chen, how do we get diffusion coefficient at a different temperature? That's something we're going to talk about a little bit later. Okay?